For centuries, light was treated as something fundamentally different from the forces that made compasses turn or sparks jump between metals. Light illuminated the world, revealed colors, and defined vision itself, while electricity and magnetism seemed confined to laboratories, storms, and navigation tools. These phenomena lived in separate intellectual worlds. Scientists studied optics on one side and electrical or magnetic effects on the other, rarely suspecting that they were expressions of the same underlying reality. This separation felt natural because the human senses reinforced it. Light could be seen, electricity could shock, magnetism could attract or repel. Nothing in everyday experience suggested a deep unity between them. This conceptual divide began to weaken in the early 19th century, as experiments hinted that electricity and magnetism were related. Electric currents could deflect magnetic needles, and changing magnetic fields could induce electric currents. These discoveries were revolutionary, but they still stopped short of explaining light. Light remained mysterious. Was it made of particles, as Isaac Newton believed, or waves, as others argued? And if it was a wave, what exactly was waving? There was no obvious medium, no vibrating substance one could point to. Into this uncertainty stepped James Clerk Maxwell, whose greatest insight was not tied to a single experiment, but to a radical act of synthesis. Maxwell approached nature with the conviction that its laws must be coherent and unified, even if that unity was hidden beneath layers of complexity. He took the scattered experimental results of his time and translated them into a mathematical language that could reveal connections invisible to intuition alone. Maxwell realized that electricity and magnetism were not static forces acting instantaneously at a distance, but dynamic processes unfolding through space. When an electric field changes, it gives rise to a magnetic field, and when a magnetic field changes, it generates an electric field. This mutual generation forms a self-sustaining dance, a continuous exchange that can propagate through empty space. Once written mathematically, this interaction revealed something astonishing. The equations describing these changing fields predicted the existence of waves. These waves were not mechanical vibrations like sound waves in air or water waves on the sea. They did not require a physical medium. Instead, they were oscillations of electric and magnetic fields themselves, rippling outward at a fixed speed determined by fundamental constants of nature. When Maxwell calculated this speed, he found that it matched the measured speed of light. The conclusion was unavoidable. Light was not a separate phenomenon at all. Light was an electromagnetic wave. This idea collapsed centuries of separation in a single stroke. Light, electricity, and magnetism were no longer different categories of phenomena. They were different manifestations of the same underlying field. What humans perceived as brightness or color was simply a narrow slice of a much broader electromagnetic spectrum, most of which lay beyond direct human perception. The visible rainbow was just a small window into a vast, invisible world of waves. The unification of light with electricity and magnetism changed how scientists understood reality itself. It suggested that nature was governed by deep principles that could connect phenomena across vastly different scales and experiences. Something as gentle as sunlight and something as violent as lightning were revealed to be expressions of the same fundamental laws. This was not just a technical achievement, it was a philosophical transformation. Crucially, Maxwell's unification was predictive, not merely descriptive. He did not start with known electromagnetic waves and label them as light. Instead, his equations predicted waves that had never been observed. Light was simply the one example humans already knew. This meant there had to be other electromagnetic waves with longer and shorter wavelengths, traveling invisibly through space. Decades later, experiments confirmed this prediction, uncovering radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. Every one of them fit seamlessly into the framework Maxwell had created. This unification also reshaped humanity's relationship with space itself. Before Maxwell, action at a distance was a troubling mystery. How could forces act across empty space with no apparent mechanism? Maxwell replaced this discomfort with the concept of fields entities that exist throughout space and carry energy, momentum, and information. Light was no longer something that jumped instantaneously from source to observer. It was a process, unfolding through space and time, obeying precise mathematical laws. The consequences of this insight reached far beyond physics textbooks. Once light was understood as an electromagnetic wave, it became possible to manipulate and generate similar waves intentionally. Communication no longer required wires stretching across continents. Information could be encoded into electromagnetic signals and sent through the air. Radio, television, radar, and wireless communication all trace their origins back to this single act of unification. Every time a signal travels invisibly from a transmitter to a receiver, it is following the path Maxwell revealed. Equally important was the way this unification influenced later scientific thought. When 20th century physicists grappled with the nature of space and time, Maxwell's equations stood firm. They refused to conform to older notions of absolute time and space, forcing a reevaluation of these concepts. This tension played a crucial role in the development of modern physics, showing once again that the unification of light with electricity and magnetism was not a closed chapter, but an open doorway. At a deeper level, the unification of light with electromagnetic forces changed humanity's self-understanding. It revealed that what we perceive is limited not by the universe, but by our senses. The world is filled with waves passing through us at every moment, unseen and unfelt, yet carrying immense power and information. Light, once thought to be unique and special, became a familiar member of a much larger family. Maxwell's achievement reminds us that the most profound revolutions do not always arrive with noise or spectacle. Sometimes they come quietly, through symbols written on paper, revealing that the universe is simpler and more unified than it appears. By showing that light is an electromagnetic phenomenon, he did more than solve a scientific puzzle. He demonstrated that nature, at its deepest level, speaks with one voice, and that through mathematics, humanity can learn to hear it. In the 19th century, physics stood at a crossroads between hands, on experimentation and abstract reasoning. Laboratories were full of coils, batteries, magnets, and wires. Scientists observed sparks, measured currents, and noted how needles moved. But these observations often lived as isolated facts rather than parts of a single, coherent picture. Many great experimentalists of the era uncovered crucial pieces of nature's behavior, yet the deeper meaning behind those results remained fragmented. The challenge was not the lack of data, but the lack of a unifying language capable of turning scattered experiments into universal laws. This was the intellectual landscape into which James Clerk Maxwell entered. Unlike many of his contemporaries, Maxwell was not driven primarily by building new instruments or performing dramatic demonstrations. His true laboratory was the page. He possessed a rare ability to look at experimental results produced by others and see not just what happened, but what had to be true beneath the surface. For Maxwell, experiments were not endpoints. They were clues pointing toward deeper structures. Before Maxwell, scientists like Faraday had revealed astonishing behaviors of electricity and magnetism. Electric currents could generate magnetic effects, and moving magnets could induce electric currents. Faraday, in particular, introduced the revolutionary idea of lines of force, imagining space filled with invisible structures guiding electrical and magnetic interactions. Yet Faraday struggled to express these ideas mathematically. His genius was intuitive and visual, while the mathematical formulation lagged behind. Many physicists admired his experiments, but dismissed his conceptual language as vague or unrigorous. Maxwell saw something different. Where others saw rough metaphors, he saw the outline of a precise theory waiting to be written. He believed that mathematics could give Faraday's insights the clarity and power they deserved. This required a bold leap, treating fields as real physical entities rather than mere calculation tools. At the time, this was far from obvious. Forces were often thought to act directly between objects, instantaneously and mysteriously. The idea that space itself could carry physical properties felt strange, even uncomfortable. Maxwell's leap was to trust mathematics as a bridge between experiment and reality. He did not simply fit equations to known data. He built a framework in which the equations expressed the inner logic of physical processes. Each term in his equations corresponded to something meaningful in the physical world: electric fields, magnetic fields, charges, currents, and their changes over time. Mathematics became a map of nature's behavior, not just a bookkeeping device. This approach marked a turning point in the philosophy of science. Instead of asking only what happens when a wire is moved or a current flows, Maxwell asked how all such phenomena must be connected if nature is consistent. Experiments provided constraints, but mathematics revealed necessity. If certain experimental facts were true, then certain mathematical relationships had to hold. And if those relationships held, then new phenomena had to exist, whether or not anyone had observed them yet. The most striking outcome of this leap was the realization that changing electric and magnetic fields naturally generate one another. This was not obvious from experiments alone. It emerged from the structure of the equations themselves. Maxwell noticed that the existing laws were incomplete unless an additional term was added, one that accounted for a changing electric field producing magnetic effects even in empty space. This was a subtle mathematical insight, but its physical implications were enormous. With this addition, the equations became consistent, and something remarkable happened. They no longer merely described static or slowly changing situations in laboratories. They predicted the possibility of waves traveling through space, sustained by the mutual interaction of electric and magnetic fields. No experiment at the time demanded such waves. They appeared because the mathematics required them. This was a radical shift in how scientific knowledge could be generated. For the first time, equations were not just summarizing known behavior. They were revealing hidden aspects of reality. Maxwell had crossed a boundary. He showed that mathematics could act as an exploratory instrument, capable of probing realms beyond direct observation. This leap would later become a defining feature of modern physics, from relativity to quantum mechanics. Equally important was the discipline Maxwell imposed on theoretical reasoning. His equations were not arbitrary constructions. Every symbol carried physical meaning, and every relationship could be traced back to experimental roots. This balance between abstraction and empirical grounding gave his work extraordinary durability. Even as technology advanced and experimental precision increased, Maxwell's framework remained intact. The leap from experiments to mathematical laws also transformed how scientists thought about explanation. Instead of relying on mechanical models or analogies, physics could now explain phenomena through structure and symmetry. The question shifted from what mechanism pushes this object to what equations govern this process. This was not a retreat from reality, but a deeper engagement with it. The equations were not replacing nature. They were revealing its internal grammar. This new style of thinking influenced generations of scientists. It taught them that understanding does not always come from watching phenomena more closely, but from seeing how different observations must fit together. Maxwell's work showed that unity is not something imposed by human preference, but something discovered through careful reasoning. When experiments appear disconnected, it may be because the unifying framework has not yet been found. The practical consequences of this leap were immense, but its intellectual consequences were even greater. By elevating mathematics to a central role in physical theory, Maxwell helped redefine what it means to know something scientifically. Knowledge was no longer confined to what could be directly seen or touched. It included what could be logically inferred from well-tested principles. In hindsight, this transition seems almost inevitable, but at the time it required extraordinary confidence. Maxwell had to trust that the abstract structures he was building corresponded to something real in the world. History vindicated that trust. Experiments conducted years later confirmed predictions that emerged purely from mathematical reasoning. This moment marked the birth of a new scientific method, one in which experiments and equations work in tandem, each guiding and correcting the other. Maxwell did not abandon experimentation. He transcended it by embedding it within a deeper theoretical vision. Through this leap, physics gained a powerful new way of seeing the universe not just as a collection of phenomena, but as a coherent system governed by elegant, far-reaching laws. In the history of science, few ideas have achieved power through such extreme simplicity. 4 compact mathematical statements, written with symbols that could fit on a single page, reshaped humanity's understanding of nature. These equations did not describe a single experiment, a single device, or a single phenomenon. Instead, they captured the behavior of electricity, magnetism, and light across the entire universe. They revealed that forces once thought separate were, in fact, different expressions of one unified reality. When James Clerk Maxwell brought these equations together, he was not merely summarizing known facts. He was distilling decades of experimental discoveries into a framework that exposed their hidden structure. Before this moment, electrical and magnetic laws existed as a collection of separate rules. Some explained how charges produced electric effects, others described how currents generated magnetism, and still others accounted for induction. Each law worked in its own domain, but there was no single vision tying them together. What made Maxwell's formulation revolutionary was not just what it included, but how it was organized. Each equation expressed a fundamental principle about how fields behave in space and time. One showed how electric charges create electric fields. Another described the absence of isolated magnetic charges, revealing magnetism as inherently linked to motion and loops. A third captured how changing magnetic fields generate electric effects. Final equation, the most radical of all, revealed that changing electric fields also generate magnetic effects, even in empty space. That last insight was the turning point. Without it, the system would have remained incomplete. With it, the equations became self-sustaining. They described a universe in which electric and magnetic fields are not passive consequences of matter, but active entities that interact with one another. When one changes, it gives rise to the other, and this mutual interaction allows disturbances to propagate outward as waves. From this structure emerged a stunning consequence. When Maxwell analyzed the equations mathematically, he discovered that they predicted waves traveling through space at a fixed speed. That speed was not inserted by hand. It arose naturally from the constants already present in electrical and magnetic measurements. When Maxwell calculated its value, he found that it matched the known speed of light. The implication was unavoidable. Light itself was an electromagnetic phenomenon. This was not a reinterpretation of existing observations. It was a revelation born entirely from the equations. Light, something humans had studied for millennia, was suddenly explained as a vibration of invisible fields. Even more astonishing was what followed logically. If light was one kind of electromagnetic wave, then there had to be others, waves with frequencies too low or too high for human eyes to detect. The equations demanded their existence long before experiments confirmed them. The power of these equations lay in their universality. They applied equally to a spark in a laboratory, a lightning bolt in the sky, sunlight reaching Earth from the sun, and signals traveling across vast distances in space. They made no distinction between the small and the large, the artificial and the natural. As long as electric charges and currents were involved, the same laws governed everything. Equally transformative was the shift in how physics understood causality. Before Maxwell, forces were often treated as instantaneous actions at a distance. His equations replaced that picture with one in which influences propagate through space at a finite speed. Changes do not happen everywhere at once. They travel. Space itself becomes an active participant in physical processes, carrying energy and information through fields. This new view altered the very concept of reality in physics. Fields were no longer mathematical conveniences. They became fundamental entities. Energy could exist not just in objects, but in space itself. Light was no longer a mysterious substance or a stream of particles alone, but a dynamic process unfolding through electromagnetic fields. The elegance of the equations also set a new standard for scientific explanation. Instead of relying on complex mechanical models filled with gears and hypothetical media, physics could now explain phenomena through symmetry, structure, and mathematical necessity. The equations did not tell stories in words. They expressed relationships that held everywhere and always. This was a profound change in how understanding itself was defined. As experimental techniques advanced, the equations proved astonishingly resilient. New discoveries did not overthrow them. Instead, they confirmed their accuracy again and again. Radio waves, microwaves, X-rays, and gamma rays all fit seamlessly into the same framework. Each new form of electromagnetic radiation was not a surprise to the theory, but a validation of it. The influence of these equations extended far beyond electromagnetism. They shaped the development of modern physics by revealing tensions with older ideas of space and time. When physicists later realized that the speed predicted by the equations was the same for all observers, regardless of motion, it forced a reconsideration of fundamental assumptions. This tension played a crucial role in the birth of new theories that reshaped 20th century science. Yet, for all their abstract beauty, the equations also had concrete consequences. They made possible the deliberate generation and control of electromagnetic waves. Communication technologies, imaging systems, navigation tools, and countless modern devices rely directly on principles encoded in these four statements. Every wireless signal, every broadcast, and every data transmission through space is governed by the same laws Maxwell wrote down. What makes this achievement extraordinary is its compression of meaning. An immense range of physical behavior is captured in a form so concise that it almost seems magical. The equations do not merely describe nature, they reveal its underlying logic. They show that complexity can arise from simple rules, and that profound unity can exist beneath apparent diversity. In the end, these four equations changed physics forever, not because they answered every question, but because they showed what a complete and unified theory could look like. They demonstrated that mathematics, when guided by experimental truth and physical insight, can uncover realities far beyond direct perception. Through them, light was no longer just seen, it was understood. Long before antennas rose into the sky or radios crackled with distant voices, the existence of invisible waves traveling through empty space was nothing more than a daring implication of mathematics. No one had seen them, no one had measured them, and no instrument of the 19th century was capable of detecting them. Yet they existed on paper, emerging inevitably from a set of equations written by James Clerk Maxwell. This moment marked one of the most extraordinary acts of prediction in the history of science, the discovery of something real before it was ever observed. At the time, physics was still deeply rooted in what could be directly sensed or experimentally demonstrated. Phenomena were considered trustworthy only when they could be seen, heard, or measured with existing tools. The idea that mathematics alone could reveal a hidden aspect of reality felt almost unscientific to many. Equations were supposed to describe experiments, not outrun them. Maxwell quietly overturned this expectation. While refining his theory of electricity and magnetism, Maxwell noticed that the equations did something unexpected. They allowed for self-sustaining disturbances, ripples formed by electric and magnetic fields, continuously generating one another. These disturbances did not require wires, charged particles, or material media. They could travel through empty space. When Maxwell worked out the speed of these ripples, the number stunned him. It was identical to the measured speed of light. This result was not engineered to match known facts. Maxwell did not adjust his equations to force agreement with optics. The speed emerged naturally, dictated by constants already measured in electrical and magnetic experiments. At that moment, a profound realization crystallized. Light itself was one example of a much broader class of electromagnetic waves. What made this leap truly radical was that it extended far beyond light. If the equations allowed waves of one frequency corresponding to visible light, then they must also allow waves of other frequencies. Some would be slower and longer than light waves, others faster and shorter. Most of them would lie entirely beyond human perception. The universe, Maxwell realized, was filled with unseen motion. This was not speculation in the loose sense. It was a logical necessity imposed by the mathematics. If the equations were correct, and every known experiment supported them, then these waves had to exist. Nature had no choice. Reality was larger than observation. For years, these waves remained purely theoretical. Many physicists admired Maxwell's equations, but hesitated to accept the physical reality of unseen electromagnetic waves. Without experimental proof, the idea lingered in a gray zone between bold insight and mathematical curiosity. Yet Maxwell never expressed doubt. For him, the consistency and coherence of the theory were evidence enough. This confidence represented a turning point in scientific thinking. For the first time, equations were trusted not only to explain what had already been measured, but to reveal what had not yet been discovered. Mathematics became a kind of telescope for the invisible, capable of extending human knowledge beyond the reach of the senses. Eventually, experiments caught up. Decades later, electromagnetic waves outside the visible spectrum were detected and generated in laboratories. Radio waves, in particular, confirmed Maxwell's prediction with striking clarity. Signals could be sent through space without wires, exactly as the equations had implied. What had once existed only as symbols on a page now filled the air, carrying information across vast distances. This confirmation did more than validate a theory. It permanently changed the relationship between theory and experiment. Maxwell's success demonstrated that reality could be explored through reasoning alone, provided that reasoning was grounded in well-tested principles. The universe was shown to be intelligible even in regions humans could not directly perceive. The prediction of invisible waves also reshaped humanity's understanding of space itself. Empty space was no longer empty. It became an active arena where fields oscillate, energy flows, and information travels. Light was no longer a mysterious entity emitted and absorbed by matter. It was a process unfolding continuously through space and time. This shift had deep philosophical consequences. It challenged the idea that what is real must be visible. It suggested that human perception samples only a tiny fraction of what exists. The electromagnetic spectrum, now known to stretch from long radio waves to ultra-short gamma rays, revealed a universe vastly richer than everyday experience suggests. Technologically, the impact was transformative. Once invisible waves were understood and harnessed, they became the backbone of modern civilization. Communication, navigation, medical imaging, astronomy, and countless other fields rely on electromagnetic waves beyond visible light. Every wireless signal is a quiet tribute to that original mathematical prediction. What makes this achievement remarkable is its restraint. There was no dramatic announcement, no immediate acclaim. Maxwell simply followed the logic of his equations wherever it led, even when it led beyond the known world. He trusted that nature would eventually confirm what mathematics had revealed. In predicting invisible waves, Maxwell showed that science does not advance only by looking harder at what we can see, but by thinking more deeply about what must be true. He expanded reality itself, revealing that the universe is not limited to human senses, and that its most profound truths may first appear not in experiments, but in equations. When the first telegraph wires stretched across continents, they were seen as marvels of engineering rather than expressions of deep physical law. Messages that once took weeks could suddenly travel in minutes, encoded as electrical pulses racing through metal lines. Yet, even this early revolution depended on an incomplete understanding. Signals weakened over distance, interference appeared mysteriously, and engineers relied on trial and error to solve problems they could not fully explain. Beneath the surface, the behavior of those signals followed rules that had already been written down by James Clerk Maxwell, even if the engineers themselves did not yet realize it. Maxwell's work quietly transformed technology by revealing how electromagnetic signals truly behave. His equations showed that electrical disturbances do not merely flow through wires. They interact with space itself. Signals propagate as waves, carrying energy and information through electromagnetic fields. This insight explained why long telegraph cables behaved unpredictably and why signal speed and distortion depended on fundamental properties rather than simple mechanical factors. Over time, these principles allowed engineers to design better cables, amplifiers, and transmission systems, turning fragile early networks into reliable global infrastructures. As communication technology advanced, wires were no longer seen as necessities but as limitations. Maxwell's prediction that electromagnetic waves could travel through empty space opened an entirely new possibility: communication without physical connections. When radio transmission became practical, it did not emerge as a lucky accident. It was the direct realization of a theoretical framework that had already described how waves could be generated, transmitted, reflected, and received. Antennas, circuits, and receivers were all built to align with laws discovered decades earlier. This shift marked a profound change in how humans interacted with distance. Information was no longer tied to physical paths carved across land and sea, voices, music, and data could spread outward in all directions, crossing borders and oceans with ease. Broadcasting transformed culture, politics, and entertainment, creating shared experiences on a scale never before possible. Behind every broadcast signal was the same invisible structure of fields and waves described in Maxwell's theory. The progression from radio to television, radar, and satellite communication followed naturally. Each new technology explored a different region of the electromagnetic spectrum, but all obeyed the same underlying principles. Radar systems used reflected waves to detect distant objects, altering warfare, aviation, and weather forecasting. Satellites extended communication beyond Earth itself, wrapping the planet in a shell of continuous connectivity. None of these developments required new fundamental laws, only new ways to apply existing ones. As electronics evolved, Maxwell's influence became even more deeply embedded. The design of circuits, transmission lines, and signal processors depends on understanding how electromagnetic fields distribute energy and interact with materials. At high frequencies, signals no longer behave like simple currents flowing through wires. They behave like waves guided by structures. Modern engineers routinely solve problems that Maxwell's equations describe with precision, often without explicitly writing them down, yet always relying on their implications. The rise of digital communication did not diminish this legacy, it intensified it. Binary data, compressed streams, and encrypted signals still ride on electromagnetic waves. Whether information is encoded as analog variations or digital pulses, it must be transmitted, guided, and received according to the same physical laws. Fiber optic cables, which carry light instead of electrical currents, represent a direct embodiment of Maxwell's unification of light and electromagnetism. Data moves as pulses of light, controlled and predicted using principles rooted in his work. Wireless networks pushed this transformation into everyday life. Wi-Fi, cellular networks, and Bluetooth technologies rely on precise control of electromagnetic waves in crowded spectral environments. Devices constantly negotiate interference, reflection, and absorption, all phenomena governed by Maxwell's framework. The ease with which information now flows masks the complexity beneath it. A simple message sent from a phone involves fields oscillating billions of times per second, interacting with buildings, the atmosphere, and countless other signals. Beyond communication, the same principles underpin medical imaging, navigation systems, remote sensing, and scientific instruments. Magnetic resonance imaging uses controlled electromagnetic interactions to probe the human body. Global positioning systems depend on electromagnetic signals synchronized with extraordinary precision. Astronomy explores the universe across the electromagnetic spectrum, revealing objects invisible to optical telescopes alone. What makes this technological lineage remarkable is its continuity. There is no sharp break between 19th century theory and 21st century devices. The same equations that explained sparks and magnets now govern data centers, smartphones, and space probes. Technology did not outgrow the theory, it grew into it. This continuity also reshaped how innovation happens. Engineers no longer rely solely on experimentation and incremental improvement. They design systems by solving equations that predict behavior before anything is built. This predictive power reduces uncertainty and accelerates progress, allowing complex systems to function reliably at global scales. From the first telegraph click to a modern wireless signal, the journey of information follows paths laid down by electromagnetic law. What began as an abstract unification of forces became the invisible infrastructure of modern life. Every message sent through the air is a quiet confirmation that ideas once confined to notebooks now shape how humanity connects, communicates, and understands the world. At the dawn of the 20th century, physics appeared nearly complete. Many scientists believed that the fundamental laws of nature had already been discovered, and that the future of the field lay only in refining measurements. Yet beneath this confidence lay a quiet tension, created by a set of equations that refused to fit comfortably within older ideas of space and time. Those equations were the legacy of James Clerk Maxwell, and they would become the catalyst for one of the greatest revolutions in scientific thought. Maxwell's equations described electromagnetic waves traveling through space at a fixed speed. What made this troubling was not the speed itself, but its stubborn independence from the motion of the observer. According to classical mechanics, speeds should add and subtract depending on how fast someone is moving. Yet Maxwell's framework made no such allowance. The speed of electromagnetic waves emerged as a constant of nature, built directly into the structure of the equations. No matter how one moved, the equations insisted on the same result. This inconsistency created a deep conceptual crisis. Physicists could not simply discard Maxwell's work. It had been confirmed repeatedly by experiments and underpinned emerging technologies. Instead, they were forced to question assumptions that had stood unchallenged for centuries. Concepts such as absolute space and absolute time, inherited from Newtonian physics, suddenly looked fragile. It was into this crisis that Albert Einstein stepped. Rather than modifying Maxwell's equations to fit older ideas, Einstein chose the opposite path. He treated the equations as fundamentally correct and allowed space and time themselves to change. This decision led directly to the theory of special relativity, in which measurements of time and distance depend on the motion of the observer, while the speed of light remains constant for all. In this way, Maxwell's work did not merely influence relativity, it demanded it. Without the electromagnetic framework, there would have been no compelling reason to abandon classical notions of time and space. Maxwell's equations were the immovable object against which old physics shattered. Einstein later acknowledged this debt, recognizing that his insights were built on foundations Maxwell had laid decades earlier. The influence did not stop with relativity. Maxwell's field-based view of nature reshaped how physicists thought about forces and interactions. Instead of imagining direct pushes and pulls between objects, modern physics increasingly described reality in terms of fields permeating space. This perspective became essential in the development of quantum theory, where particles and fields blur into one another, and interactions are governed by probabilities rather than certainties. Quantum electrodynamics, one of the most successful theories in the history of science, is essentially a quantum version of Maxwell's classical ideas. It retains the concept of electromagnetic fields, but merges them with quantum principles, achieving predictions of astonishing accuracy. The structure of this theory still echoes Maxwell's original framework, demonstrating how deeply his ideas are embedded in modern physics. Even attempts to unify all fundamental forces draw inspiration from his achievement. Maxwell showed that forces once thought unrelated could be understood as manifestations of a single underlying principle. This success became a model for later unification efforts, encouraging physicists to search for deeper connections between gravity, electromagnetism, and the forces governing subatomic particles. The dream of a unified theory owes much to the precedent Maxwell set. Beyond specific theories, Maxwell's legacy shaped the scientific mindset itself. He demonstrated that equations could reveal realities not yet observed, and that consistency and symmetry were powerful guides to truth. This approach became a defining feature of 20th century physics, theories were judged not only by their ability to explain known data, but by their internal coherence and predictive power. This shift also altered how scientists understood the relationship between mathematics and the physical world. Mathematics was no longer seen as a convenient descriptive tool, but as a language capable of expressing the universe's deepest structure. Maxwell's equations suggested that nature itself is written in mathematical form, waiting to be deciphered. The reach of this influence extends to cosmology, particle physics, and even emerging theories of spacetime itself. Concepts such as fields, waves, and invariance under transformation trace intellectual lineages back to Maxwell's work. Even when his equations are modified or extended, their spirit remains present. What makes this legacy remarkable is its continuity. From 19th century electromagnetism to modern theories of spacetime and quantum interactions, there is a clear thread of ideas evolving rather than breaking. Maxwell did not close a chapter in physics. He opened several new ones, each building upon the last. In shaping the thinking of Einstein and countless others, Maxwell transformed physics from a collection of laws about objects into a deeper exploration of structure, symmetry, and fundamental principles. His influence reminds us that true revolutions often begin not with dramatic experiments, but with ideas so powerful that everything built afterward must take them into account. Every day, without thinking about it, people move through a world shaped by ideas conceived more than a century ago. Light switches illuminate rooms instantly, phones connect voices across continents, satellites guide journeys, and invisible signals flow constantly through the air. These experiences feel ordinary, almost mundane, yet beneath them lies a profound intellectual legacy that continues to govern how modern life functions. At the center of this legacy stands James Clerk Maxwell, whose insights remain woven into the fabric of contemporary civilization. Maxwell's work endures because it did not solve a temporary problem or serve a narrow purpose. It revealed a structure of nature so fundamental that everything built afterward had to align with it. His equations describe how electromagnetic fields behave, how energy moves through space, and how information can be carried without physical contact. These are not historical curiosities. They are active principles operating continuously around us, whether we are aware of them or not. One reason his ideas remain relevant is their universality. The same laws that describe a beam of sunlight entering a window also govern the signals that allow a phone to stream a video or a spacecraft to send data back to Earth. Technologies evolve, materials improve, and devices become smaller and faster, but the underlying behavior of electromagnetic fields does not change. Engineers and scientists may not always write Maxwell's equations explicitly, yet every design implicitly respects them. This permanence has given modern technology a rare kind of stability. Unlike inventions that become obsolete as new principles replace old ones, electromagnetic theory has only grown in importance. As society becomes more dependent on communication, sensing, and energy transfer, the relevance of Maxwell's framework deepens rather than fades. Each new generation of technology explores the same laws in more sophisticated ways. Beyond technology, Maxwell's influence shapes how humans understand the world intellectually. His work teaches that reality often extends far beyond direct perception. Most of the electromagnetic spectrum is invisible to human senses, yet it dominates how information, energy, and structure move through the universe. This realization has altered how people think about knowledge itself. What we see is no longer assumed to be the whole story. Instead, unseen processes are recognized as equally real and often more significant. This perspective has practical consequences. Medical imaging relies on electromagnetic interactions invisible to the naked eye to reveal the interior of the human body. Astronomy uses non-visible wavelengths to study distant galaxies, uncovering phenomena that light alone could never show. Environmental monitoring, climate science, and security systems all depend on detecting and interpreting electromagnetic signals beyond ordinary vision. In each case, Maxwell's insights make the invisible readable. There is also a deeper philosophical legacy. Maxwell demonstrated that mathematics can reveal truths about nature that observation alone cannot reach. His confidence in equations as guides to reality reshaped scientific thinking. Today, scientists routinely trust mathematical consistency and symmetry to lead them toward discoveries, even when experimental confirmation lies years or decades away. This approach, now standard in physics, owes much to the success of Maxwell's vision. His work also reminds us that progress does not always arrive loudly. Maxwell did not invent a famous machine or build a public monument. His contribution was quiet, precise, and abstract, yet its impact surpasses that of many more visible achievements. This challenges common assumptions about innovation, suggesting that the most transformative ideas may emerge from deep understanding rather than immediate application. In everyday life, this legacy appears in subtle ways. When a wireless connection remains stable in a crowded city, when navigation systems maintain accuracy across the globe, or when data moves securely through fiber optic networks, it is because engineers are working within a framework that accurately describes how fields and waves behave. Failures often occur not from a lack of creativity, but from ignoring or misunderstanding these fundamental constraints. Maxwell's ideas also shape the future. As humanity explores quantum technologies, advanced communication systems, and deeper space exploration, electromagnetic theory continues to provide the foundation. Even as new theories extend or refine our understanding, they do so by building upon, not discarding, the principles Maxwell established. His work acts as a reference point, a standard against which new ideas are measured. Perhaps the most remarkable aspect of this legacy is its invisibility. The success of Maxwell's ideas has made them fade into the background of everyday awareness. People rarely think about electromagnetic fields when sending a message or turning on a device. The laws function so reliably that they feel natural, almost inevitable, yet this very invisibility is a sign of their power. They have become part of the world's hidden infrastructure, operating continuously without attention. In the end, Maxwell's lasting influence lies not only in what he discovered, but in how deeply his discoveries have been absorbed into modern life. His vision transformed abstract equations into the silent architecture of a connected world. Long after the context of the 19th century has faded, the principles he uncovered continue to shape how humanity communicates, explores, and understands reality itself.